Hello everyone, welcome to lecture number 18. Today's topic is computing platforms. Last time we talked about a hybrid database architecture that can be used for Twitter. We showed basically the original design, which was kind of logical and efficient, using a relational database, but had really slow reads because it involved joining multiple tables and there was a read. Solution to that problem was to use a NoSQL database to pre-build feeds for users. That design made the reads fast, but writes were slow and there was duplication. Those are things that we accepted, but in particular for celebrities that have a lot of followers, slows became really slow in that design. So the final result was a combination of the two, and so this is a new idea. Storing the exact same data in two different kinds of databases, just having a subset of the user's data in one type versus the other, because you have a diversity in your users. Some of the users, we call them consumers, have a lot more reads rather than writes, whereas celebrities, when they use the system, the impact of their writes is much greater on the system as a whole compared to the impact of their reads. So it makes sense to put them in a relational database instead of a NoSQL database. All right, now today we're going to be talking about computing platforms. I'm going to start off by talking about a general problem of distributing your code or your service, right? In general, packaging an app and distributing it and also deploying it is tricky and has always been tricky, because when you write an app, unless you're doing something really simple, if you're doing something that's at least moderately complex, there's some kind of specific environment required to get your code to run. Because these days you don't write everything from scratch. You make use of a lot of libraries and environments and other tools to get your work done, right? So as a developer, that's useful, but then when it comes time to run your code, it can be challenging to create the exact same environment that you had when you were developing the code to run again. So replicability of your environment is a challenge that we're going to be looking at today from a few different angles. So when we talk about the environment for an application, it means several different things. So first of all, if you're talking about a service, usually there's some kind of a server, a framework, or a middleware that runs your code. Examples of that are Tomcat, Express, or Django would be another example. So web servers, Apache. There might be code that compiles or interprets your language, or is the runtime system for your language. So for example, a certain version of Python or a certain version of the Java virtual machine. Node.js is another example. Depending on what language you're using, you need that additional code to be there to run it. In addition, you need libraries available to your code running in that language. And there are, of course, standard libraries that come with whatever version of the language you're using. But I'm talking now about third-party libraries, which have to be either downloaded or loaded with some kind of package manager like Maven or NPM or pip, or perhaps linked with LD if you're using C++ or something like that, or C. There also might be command line tools you're using. So for example, ImageMagick is a image conversion tool that very often is used in a lot of projects, and it's invoked on the command line. You might be interacting with a database on your machine like MySQL, or using OpenSSL for doing things like generating keys. Just like a whole variety of different programs that provide functionality that you're not calling directly from your code as functions. So they're not really libraries, but they are command line tools that your code can trigger and get results from, or maybe interact with as a database, stuff like that. There also might be certain operating system features or configuration that your code relies on. Your code or any of these dependencies might rely on. For example, the file system might have to have a certain structure. There might be networking set up for the like a firewall configuration that needs to be set up a certain way to get your code to run. You might be using subprocesses, threads, and the way that works is different on different operating systems. There might be certain permissions that your user needs to have to get the code to work well with, for example, other processes running under the same user on the system. There's like a whole set of configurations, I guess, of the machine that might be needed to get your application to run. Okay, so So for very simple functionality, just writing code in a certain language using standard libraries is enough to get your work done, and it's pretty easy to distribute that kind of code that's very simple and just uses the built-in language functionality. But once you start to do things that are more complex, that start using libraries and features of the system, then you need to replicate that exact same environment at runtime to get your code to work. Okay, so you may have experienced as a student that you write some code and it works on your machine, but then when it comes time for it to be graded, it doesn't work in the exact same way. And if you just tell the TA that it worked on my machine, usually that's not good enough, right? Which is why when we give out homework assignments, often we tell you to run it on a particular machine, the same one that we'll be grading on. But that's not a solution to that problem. That's a workaround to the problem, right? Because we both have access to the same machine. In general, when you're writing code, you want to be able to package it up in such a way that it can be distributed and deployed anywhere. So we're going to talk about some different solutions for that today. And these are actually evolving constantly as new languages are developed and new frameworks and new libraries, new operating system functionalities. So we're going to talk about some common choices, including the Java virtual machine, what I'd call a full virtual machine, containers, and serverless functions. Those are all related to the idea of packaging, distributing, and deploying your code, although they also could be thought of as computing platforms in general. So the first option I'm going to talk about, I'm calling it option number 0, not just to be cute with programming style indexing, but also because I don't think it's a very good option in most cases. Well, actually, there are some cases where it's useful but anyways, it's the least interesting option in my opinion. Anyway, so this option is distributing a binary executable. So when I say binary executable, I mean compiled code that can simply be copied, that's distributed as one big file that you run. And the problem with this approach is that generally it requires that the environment you're running on be very similar to the one that the executable was created on. So this is in fact used for distributing apps on consumer operating systems, whether we're talking about like Windows and Mac, or even smartphones like Android and iOS, those app stores. When you download an app from an app store, you're getting a binary executable that is pretty much the same as what everyone else gets when they download the app. That's not totally true. There could be different, like a handful of different versions that are compiled for different versions of, let's say, iPhone. But in general, you're getting the same code, and it runs on that system. The reason that works, though, is because Android, iOS, Windows, and Mac, those are all operating systems that are very consistent and controlled by the distributor to make that experience really consistent for apps that are running. Okay, Windows in particular has really historically been really good at being backward compatible, so that on a current version of Windows you can run code that's really old, pretty impressively actually, like 20 years old sometimes. So the way that you distribute a binary executable, though, it's kind of a challenge, because usually an installer program is needed, like on Windows, to install not just the program, but the different configuration files and things that are needed to make the app work. I guess that's not necessarily the fault of the program. Sometimes also to install libraries. There might be an app store these days as well that takes care of that for you. That works because you're dealing with a very uniform target environment, whether it's Windows, Mac, Android, or iOS. But for developing your own code that is not running on a consumer operating system, that's running on a server in the cloud, that's generally not the situation that you face, because there are a lot of different versions of like Linux and other server operating systems you might be using. Okay, another example of distributing a binary executable would be on Linux. If you're using the distribution of Linux you use, so distribution is like, for example, Ubuntu is a distribution, or Red Hat, SUSE. Those distributions have a library of precompiled binaries for various free and open source softwares that you can install by running a command like yum or apt, and those just download from an online repository. It's kind of like a free app store that you interact with using a command line. that's been around for much longer than these consumer app stores have been around. So tools like Yum have been around for like I want to say like 15 years or so. Right? Okay, so that's option number 0. We're not going to talk too much about that. I mean, technically, like if you are developing a Windows or Mac application, like the tools that you get, whether it's Visual Studio or Xcode, are designed to compile to an application that will run on that operating system. And same thing goes for Android Studio for Android and Xcode for iOS. But if you're developing server applications, like a website or something like that, that's not generally an option. The next option, which I'm calling option number 1, is to distribute source code plus some instructions for compiling it, which I'm going to call the README. Right? This usually is a disaster because it's hard to. Most packaging technologies or compiling technologies are pretty unreliable or inconsistent, I guess, on different platforms because of the variety of platforms. So, maybe you post your code to GitHub, you write a README file that has some instructions for how to set up the environment. That might work for if you write good instructions and the user's machine is similar to yours, but there are a lot of things that can vary. You might be using a build system like Make or Rake, or you might write a bash script that runs a bunch of a series of commands. Depending on the language, there are different tools available to set up the environment. But how well those work will depend on the language, I think. And my own experience has been that it's not great. There's generally a low probability, if you distribute source code, that the user will be able to reproduce a working environment if all you give them is like a README file or one of these like language level compilation tools. So it might have worked on your machine, but it probably won't work on someone else's machine unless they're lucky or they put in a lot of work to figure out how to fix the things that go wrong when they try to compile it. Now, one exception to that, I think, is Maven and Gradle for Java code. Distributing Java source code is pretty easy because the package manager, I guess, provides jar files that are platform independent, and so you can install those without really encountering as many issues as you would with, let's say, pip installing from requirements.txt file, if we're talking about Python. Okay. The third option here, which I'm calling option number 2, is to distribute JVM bytecode. So bytecode, I think I mentioned this in the first lecture or the second lecture, is compiled Java code that doesn't compile to CPU instructions, but rather compiles to Java virtual machine instructions. And at runtime, the Java runtime environment emulates that virtual machine to translate to run that code, and it also will like compile the most frequently executed code into native code to make that efficient. The idea here is you compile your code once and run it anywhere, and so you distribute code in jar files or class files, I guess, which are inside the jar files, or WAR files. Interestingly, a lot of new languages besides Java also use the same idea and compile to the exact same JVM instruction set. So you may have heard of Scala, Kotlin, Clojure, Groovy, Jython, or JRuby. The ones you probably have heard of maybe are Scala and Kotlin and Clojure. Those languages compile to run on the same Java virtual machine that Java compiles to. The benefit of this approach is that your code is small. You only have the application itself that you're distributing. It's pretty simple and it runs with pretty good performance. The downside to your choice of languages is limited to those that compile to the Java virtual machine. Your app can experience differences in its environment in the sense that it has access to the host operating system. That host operating system can be different, and you don't have control over those outside environment features in the thing that you're distributing. You just have to hope that whatever, either you don't use anything outside the environment, and that would make it portable, or the things that you're accessing outside the environment, like on the command line, for example, are going to be the same across all your systems, which is a bad assumption. Okay. But now I'm going to switch gears a little bit and talk about the main topic of this class really is virtual machines, containers, and serverless functions as 3 different computing platforms. And those relate to things I was just talking about in the sense that they also are solutions to the problem of distributing code. They're not just solutions to the problem of distributing code, but also the solutions to the problem of deploying code to the cloud or in general on your own hardware even. So let's talk about virtual machines. So a virtual machine is it's kind of self-explanatory, right? It's not a real machine, not a physical machine, but something that emulates a physical machine, but is not a real physical machine. Okay. Before we get there, let's talk about what we had before virtual machines, which is that we had physical machines. In the old days, when I say old days here, I mean if we're looking at let's say 15 years ago and earlier, like roughly 2005 and earlier, at that point virtual machines were not that common. Although, we still had the internet and e-commerce had taken off and things like that. So in those days, you installed one operating system on a server. So you bought a server, a physical machine, installed an operating system. And what you would do is you probably would want to share that machine with several different services, perhaps. Like let's say you had one machine, you wanted to run a web server and also an email server on that same machine because the machine was fast enough to handle those 2 things. You wanted to get the most value for that machine. The way you do that is to run 2 different processes on the same machine, right? So that's like what you're used to doing on your own machine. So if you have a laptop, right, you use that machine to run several browser tabs, maybe a mail application, stream videos from Netflix, whatever. You're doing all that on one machine. You have lots of programs running at the same time. One of the big purposes of an operating system is to allow one CPU and one set of memory to be shared among many concurrent applications. Those applications are called processes. So in the operating systems class, CS-343, we talk about how that works in detail, but just take for granted that it's possible, okay? So, and in the old days, that's what you did on servers as well. So you had one physical machine running an operating system, and you had several different processes running to perform different functions, and also to provide horizontal scaling. So, for example, to have a web server that handle lots of requests, you could run lots of threads, which are kind of like similar to running lots of applications that would in parallel process lots of requests. Okay, but nowadays that approach of running more than one service on one machine, on one operating system, is kind of obsolete and rare. Instead, what we do typically is instead of breaking up a machine by sharing a machine's resources by having the operating system share a machine's resources among processes, we have a hypervisor share a physical machine's resources among several virtual machines. So a hypervisor is to virtual machines what an operating system is to processes. It's a resource manager that splits up a machine to allow many OSs to run. So if you look at this picture on the left, just this part I'm circling here, ignore the right-hand side for a second, just look at type 1. You have one piece of hardware, the hypervisor runs on that hardware, and it allows multiple operating systems to run. We call those guest operating systems, simultaneously sharing that hardware. Okay, so they each get a share of the CPUs and a share of the memory to run their own operating systems, and they kind of they look like they're running on a real machine. They think they're running on a regular machine. They don't really have to know that they're running on a virtual machine, but the amount of resources they get are less than what is available in the full machine. If you have multiple virtual machines running on a physical machine and they want to communicate to each other, they can do so using the same mechanism that 2 machines across the world communicate with each other, which is to say they can use the network to communicate. So they can send packets to each other, just like if those were different physical machines. Otherwise, there is no real connection between them apart from on the network. Okay. So those virtual machines are isolated from each other. and they get a share of their resources. Okay, so there's this hypervisor is a piece of system software similar to an operating system, but like kind of an operating system for operating systems. Examples are KVMs and VMware Hyper-V, and so on. And you also can get a hypervisor when you use the cloud. You're using a hypervisor that's provided by the cloud provider like Amazon or Microsoft or Google. Okay, we'll talk more about that in a second. So why would you do this? Why would you want to split up a physical machine into several virtual machines? When you actually have this other way of splitting resources, which is processes, right? So clearly processes provided a benefit. The ability to run more than one program at once on a machine is extremely useful, right? It allows you to have multiple things going on. It allows you to support users switching between tasks. For a server, it's also useful because it allows you to run two different, if you have a mail server and a web server running on the same machine, those are, sometimes the requests for those two are going to come in at different times. So you're able to use, when one is idle, the other could be working, right? So you're able to share the resources in an efficient manner. So, but why do we want to bother with virtual machines instead of using the process level sharing? Well, the benefit of virtual machine, there's several of them. So one of them is we have a greater degree of isolation. So keep in mind also, I have to justify this knowing that actually there's an additional level of complexity added by having virtual machines, and there's an additional bit of inefficiency compared to running on a physical machine. Because you have to there's a translation that happens between the instructions that run in the virtual machine and the instructions that happen on the physical machine. For example, memory address ranges have to be translated, things like that. Because each of the, let's say you have 3 different virtual machines, when each of them reads from memory location 0, those correspond to different locations in physical memory because the physical memory has been split up into 3 regions and assigned to the 3 different computers, 3 different virtual machines. All right, so to justify that inefficiency, we need some benefits. One of the benefits is that by isolating those machines, we can isolate problems that happen in any of this in services that are running in parallel. So for example, let's say we have the web server mail server combination. If the web server has some kind of a problem like a memory leak, a security breach, or its operating system crashes, the effects of those problems would be isolated to the one virtual machine and not affect the other. So for example, what a memory leak would cause, if these 2 programs are running on the same operating system, then the web server would consume all the memory on the machine and the mail server would have no memory available, and it would have to swap and it would be slow. So the mail server would essentially stop working just because the web server had malfunctioned. Similarly, with a security breach, if someone has access to the web server virtual machine, they do not get access to the mail server virtual machine if they're separate virtual machines. If the operating system crashes, whether it's the app's fault or the OS's fault, I guess it would be the OS's fault if it was the OS crashing. Again, the mail server could continue running. Another big benefit here is that we can migrate these virtual machines on the fly. Some hypervisors don't support this, but the most important ones do. What I mean by migration is that we can take a virtual machine that's running on one physical machine and move it quickly to another physical machine. For example, if the physical machine has to be replaced or retired or upgraded, there's some maintenance that has to happen on that physical machine, you don't have to interrupt the user. You can actually kind of like pause the virtual machine, copy the image of that virtual machine, both the memory and the disk image, to another physical machine and continue running it there without even doing like a reboot. With a reboot, it's easier, of course. You wouldn't have to copy the memory, just the disk image. Another benefit of using virtual machines is, I guess this is a benefit of sharing a physical machine among multiple services. This could apply both to virtual machines and to processes, but it's important to notice this. Servers these days are really big. They have lots of CPU cores. For example, the More machine that we use in this class, that has 48 CPU cores. It has 256 gigabytes of RAM. That should be an F of RAM. For most applications, you don't need all of that to run your own application. So, for example, the server that runs my website, it needs less than 1 CPU core and about half a gigabyte of RAM. So with this big machine here, we could run maybe 500 websites that are as popular as mine is. Okay, you'd want to, if you didn't have the ability to split up that big machine, you wouldn't be able to get the low cost of running a website, right? And if you are in the business of by using if you have different users who don't trust each other, don't want to have to coordinate, and for example, they're different customers, then creating virtual machines is really beneficial. So for example, to run my little website, rather than having to buy a big physical machine, I can actually rent a fraction of one machine from a cloud provider. In particular, I can get like a T2.micro instance or nano instance, pay a few dollars a month for it, and the cloud provider can give me root access to that machine, so I can do whatever I want on it. I can read all the files, read all the memory. I have full permissions on that. I can get full permission to just a small slice of that machine, and others can use the rest of it, and they can rent the rest of the machine without interfering with each other. Okay, if it was just a single operating system that I had login and access to, and other customers had login access to, that would be a way to split the resource. But then we would not, as customers, have root access to the machine to do whatever we wanted with it. Okay. Another benefit of virtualization is that you can start small with a small instance and scale vertically. So for example, if my website becomes more popular and I need more than one CPU core or more than half a gig of memory, I can ask for a bigger virtual machine. I can ask to be migrated to a bigger virtual machine, and by just rebooting my OS, I can get access to that additional CPU cores or additional memory. The hypervisor can manage that for me. Okay. So virtual machines are useful, and there are businesses built around that. So in particular, Amazon Web Services, AWS, started in 2006 with the EC2 service, which is Elastic Compute Cloud. That service is a service for renting virtual machines. Originally, it was just virtual machines, and nowadays, of course, AWS grew out of that to include EC2 as well as other services. What's interesting here, actually, if you look at the history, Amazon was certainly not the first company to sell the idea of server management. So the benefit of renting an EC2 instance is that you don't have to buy your own physical machine. You don't have to set it up. You don't have to have a physical location. You don't need electricity and an internet connection and cooling and all that stuff, a rack. Instead, someone else manages the hardware for you. You just get login access to do whatever you want with the software. Before 2006, there were companies that had servers, and they would rent you a server. The difference was that they weren't using virtualization. So you would have to rent a whole machine. So there are two downsides of that, though. The first one is that I have to pay for a full machine, whereas in reality I might only need a small fraction. Okay, so that's one downside. The other downside is that if you're renting a whole machine, it's harder to bill with fine granularity. So like the way it would work in the old days with previous companies like this is that you would rent a machine for a whole month, and you pay by the month, right? So the reason for that was that they had to actually install a new physical machine for you to use. So there was time. I mean, of course, they might set them up ahead of time and have them ready, but when you stopped using that machine, it would be it's harder for someone else to start using it, because they would have to install a new operating system on it and set that up for that user. With virtual machines, it became much more managing the access to those resources became much quicker. So you could actually charge by the hour for a virtual machine, which is what EC2 did. That was its big innovation, and the reason it was able to do that was because it was using it's a hypervisor rather than and giving out virtual machines rather than renting entire machines. So when you rent a virtual machine, an EC2 instance from Amazon or any other of its competitors like Azure or Google Cloud or Alibaba, then you choose the size of the machine By size, usually they're pre-configured options, but it's like the number of CPU cores, the amount of RAM, the network bandwidth. Maybe if you want to have a GPU in there, that's part of the specification of the type or size of the virtual machine. Obviously, the bigger it is, the more expensive it is. You choose the operating system you want pre-installed, and there's a library of different options you can have. Basically, any operating system you would want. Some of them are more expensive than others, if they're depending on whether they're free operating systems or proprietary. You choose the type of storage you want connected to it. The storage is also virtualized. There's typically a big pool of storage that's shared that can be like dynamically connected to the virtual machines. You specify both the type and the size, the speed and the size. And you also specify the location of the virtual machine. There are different data centers throughout the world available for you to run your instance. And the reservation period. So you can have a contract you can have no contract and just pay by the hour. You can get a 1-year contract or 3-year contract and save some money. That allows the cloud provider to know that in the future it can depend on you paying for that instance, and therefore it knows that it can maybe buy more capacity. And you also configure whether it's on the public internet or on a private network. And finally, the login credentials. If you provide an SSH public key, then you'll be able to log in to that machine without using a password. So after you specify all that stuff, a virtual machine instance is created for you within a few minutes, and then you're billed by the hour. So the range of pricing is like between roughly a third of a penny to $27 per hour. So that's a huge range. Notice the movement of the decimal point. That's between either $2 a month or $20,000 a month. Okay, so when you're setting up a virtual machine, you want to be careful not to choose one that is going to cost $20,000 a month. Because it all depends on whether you're using a tiny fraction of one machine or you're using an entire machine, and not just an entire machine, but a really expensive machine that has, for example, several GPUs connected to it that are the latest GPUs and really expensive, and a whole cluster of solid state drives and so on that can make it really expensive. Now, when you're renting virtual machines from the cloud, you don't have to worry about hardware considerations like electricity and cooling and all that stuff, and replacing hard drives when they fail. But you still have software operational concerns that you have to deal with, and those are these days called DevOps. Like that job of managing the running of the software is called DevOps. In the old days, you had sort of ops or IT, which was concerned with running the hardware and the software. But nowadays, since a lot of companies are not running their own hardware, there's this new role called DevOps, which is focused on really on just the software and the networking that's run in the cloud. Okay. And in DevOps, you have to install and configure third-party software, things like databases, web servers, libraries, distributed caches, message queues, tools. You might have to do OS updates. You have to deploy new versions of your code when they're released, and monitor the health of the code. You can monitor the health of the code by looking at log files, CPU utilization, other statistics about memory and disk usage and space, and also managing access by configuring users, setting passwords and firewalls and stuff. That's all within the purview of DevOps. So finally, I'm connecting back to what I was talking to before. So option number 3 that I'm giving for packaging up your code is to create a virtual machine. So virtual machines are a platform for code. They also are a mechanism for distributing code, in the sense that you can create a disk image for a virtual machine and then run it on a hypervisor. And as long as that hypervisor is configured with the same generic hardware that you built the machine for, the same generic network card and disk controller and the same CPU architecture, then that hypervisor will be able to run your code. And this, in fact, is a way that code is often distributed these days. Okay, so what you're shipping now, you're building a virtual machine. You might build it on your laptop, create a disk image. That disk image is a file that stores the data that corresponds to like what might be on a physical disk installed in a physical machine, but instead it's not a physical disk. It's an image that represents a virtual disk that's connected to a virtual machine that you're going to run probably in the cloud. Not necessarily in the cloud, but probably in the cloud. So that virtual hard disk image is going to be big, at least a gigabyte, maybe up to like 8 gigabytes or so. That'll include your operating system, libraries, applications that are installed, like your applications as well as third-party applications that are required for your app to run. There are different names for those. On Amazon, there are pre-configured virtual machines called AMIs, Amazon Machine Images. You also can create your own AMIs that you've customized. And those are things that you can spin up an instance with a generic operating system AMI, or you can spin up an instance with one of your own AMIs that has your software already installed, okay, to run one of your servers. Okay, so distributing your software as a virtual machine image is an option. There's some pros and cons here. So the benefit here, because we are distributing a whole operating system that is meant to run on a generic virtual machine, it's a very controlled environment. We've set up everything that needs to be set up. Like, we're not just distributing our software and hoping that the receiver provides all the supporting environment. We're actually distributing the environment and the software together. It's a huge piece of code, but it's like very self-sufficient and consistent and controlled. By using virtual machines, we know that our app will run isolated from outside applications because it has its own virtual machine. But the downside is that file we're distributing is really large because it's a whole operating system. It's a disk image. The performance of running a virtual machine, there's a little bit of overhead for running a virtual machine on top of the host operating system. And also, starting up a virtual machine is a little bit slow. It might take a couple minutes because it's booting up an operating system before running your application. So even if you want to run this code, you have to actually boot up a virtual machine and run it. And it's just, for example, as an aside, if you want to play with virtual machines, I encourage you to check out the VirtualBox software, which lets you actually run an OS on your machine. I just thought of it. I don't know if this will work, but okay, it's not going to work because I just reinstalled my OS, so ignore that. Anyway, VirtualBox is software that lets you, like, for example, run Windows on top of Mac, or run another version of Windows on top of Windows, or run Linux on top of Windows or Mac or whatever. And you can see in your file system, you can see the disk image that's created for that virtual operating system, and you can ship that disk image from your machine to another machine to run that same environment. Okay. The next option I have for distributing your code is a Docker container. And this is similar to a virtual machine, but it has some benefits. It's a newer idea. It's more efficient. And therefore, in some senses, it's better for the things it's used for, which is to distribute custom written code for services, typically. So, unlike a virtual machine, a container, one of these Docker containers is intended to run just one process. It still has its own sort of virtual machine, but it's a very stripped down virtual machine. That runs one process, yeah. So with Docker, we have containers that are defined by a Docker file. So a Docker file is a configuration file for the container that starts with a parent image. A parent image is kind of like a virtual machine image in the sense that it's a disk image, but they tend to be much smaller than full virtual machine images because they're stripped down with the intention of just running one process. They're not kind of general purpose things, and they're customized to bring in whatever. If you do need something more than just the basic stripped down Linux distribution, you have to specify it. There are a bunch of official base images available from Docker Hub. So Docker is a set of technologies, like a software for running and creating these things, as well as Docker Hub for distributing them. So here's a list of official images that are available in Docker. So like some databases. So these are containers. This is a container that gives you the Postgre database. Okay. Here's another one that gives you Mongo. Here's another one that gives you a router, another database. BusyBox is just like a very basic Linux environment. Alpine is another basic Linux environment. Ubuntu is a more full-featured Linux environment. So these are all base images. If you want to run your software, you need to choose one of these as the base for your software, and then you can modify it to run your software on top of it. Okay, so I'll talk more about that in a second. So you choose a base image. An example is Alpine is a really simple Linux distribution that's very common for Docker containers because it's very small. And here is the Docker file for Alpine. So this is like this language you're seeing here. This is for Docker files, and it starts from scratch means it's not building off of a parent image. It's starting from scratch, and instead it's starting literally from this file. So this file here, if you untar it, produces a root file system image for the Alpine operating system. Then after you extract that disk image, then you run the command /bin/sh. That is the command, the Bourne shell, the command line shell. So this basically gives you a terminal. This runs the terminal command on this Alpine Linux operating system. It's not meant to do anything useful, but rather to provide a base on which to run applications that just require a basic Linux environment and a consistent Linux environment, because this file here, whenever someone uses the Alpine base image, they'll be using this exact same, if they're using this version of the Alpine image, they'll be using this exact disk image file as the base. So if you extract this, you'll see that there are like files for all the different programs in this Linux distribution, for the kernel, there'll be a user account that's set up, all that stuff. This is like essentially a virtual machine image for this basic Linux distribution. That Alpine Linux image is only 5 megabytes in size, which is tiny for an operating system. The Ubuntu image for Docker is 190 megabytes. That's much bigger, but that actually still is really small. So this is a really stripped down version of Ubuntu. Basically, it has the kernel plus the basic, only the most basic tools that Ubuntu needs. Now, if you're using one of these base images, you would have to generally install things on top of it to make it useful. So, for example, the Postgre container, which is a relational database, the Docker file for that I'm showing here, and you can see that it starts with Alpine. It starts with the Alpine version 3.13 image, and then in addition to that, to the things I showed you before, it runs some commands to set up the environment to run this database. Okay, and all these lines here are the things that are needed to set up the Postgre database on top of Alpine Linux. And we can actually go through these one by one, and it's not terribly complicated. So the first thing it does is it creates a user Postgre that's going to be the user on which, it creates a user account to run the software. It creates a folder for storing the database. Okay, it creates another folder, sets some environment variables. That's what these are. And then it downloads the Postgre software, the open source. It downloads the source code from the web. Okay, so this here is here is where it downloads the software. It makes a folder for it. It unzips it or untars it into that folder, and then this APK command installs Linux packages. So Alpine has the APK package manager for installing. So these are tools that are needed to compile that Postgre software. For example, GCC is the C compiler. libc is needed for C. Make command is used for compile, and so on. Apparently the Perl language is also used during the compile process. And then this is the command for compiling, or a set of commands, I think, for downloading a configuration to compile. And then also this configure command starts the compiler. it generates the make file to do the compilation, sets some settings for compiling. So notice if you had just given someone the source code, here was where we got the source code. The source code itself is not enough to really make this work. There are a lot of other things you need to do. Like here, you need to install a lot of dependencies. Here, you need to create some users or a user. You have to configure the build in a certain way with certain parameters. You have to run the make and install, and then a few other things that it does to clean up, and also to like start the Postgre process and whatnot. So, and finally, this expose command opens up the firewall on the container to listen to requests on port 5432, which is how this Postgre database accepts SQL commands from the outside. So if you're developing your own software and you want to use containers to distribute it, all you have to do is bundle up your source code. Maybe you put your source code on GitHub, right? Somewhere that's public. You create a container file like the one I was showing you that starts with a base image, and you have to write out those commands that set up that environment to be able to run your code, to download your code and install it and then run it. And then that Docker image, Docker file, like I was showing you here for Postgre, anyone who has this file, just this one file, can spin up a container to run this software and to run it in the exact same way as anyone else who has this Docker file. Okay, so it creates a very consistent runtime environment for this application. All right, so you can think of this Docker file as a blueprint for the application's complete runtime environment. It's a very powerful idea. So if we want to compare containers and virtual machines, we see that containers allow several applications to run on top of an operating system, but they're doing that through Docker. You can also run more than one application on a physical machine using virtual machines. The difference is that you have a full operating system for each of those applications if it's running a virtual machine. For these Docker containers, they're not really running an operating system. They just have a translation layer between the application's view of the operating system and the real operating system. That's kind of the trick of it. And incidentally, you can run containers on top of virtual machines if you want to. You often would do that. Okay. One of the tricks of Docker to make it efficient is a Docker layered file system. So what this does is allows you to have your file system be composed of a bunch of layers built on top of your base image. So your base image here might be a certain standard distribution of Ubuntu, and then you can have an image built on top of that adds to it by making changes. But when you make changes to that base image, with this Docker layered file system, you're not actually modifying the base image, but rather you're specifying changes to that are layered on top. And so you still have a preserved copy of the base image. The benefit of that is that if you have more than one container that's using that same base image, it can reuse it by layering on top of it its own different changes. So here's an example where we have two containers with two Docker file system images. They both are running Elasticsearch. Elasticsearch makes changes to the Ubuntu base image in two steps, let's say. So this Elasticsearch image is derived from this other image. This is a Java enabled image. This Java enabled image just basically installs Java on top of Ubuntu, and Elasticsearch installs the Elasticsearch application on top. And then we have two different images built on top of it. We have the first one just sets up some configuration or just launches the Elasticsearch application, whereas the second one might have installed some configuration files and set some environment variables and then started Elasticsearch. Both of those are two different containers running Elasticsearch with different configurations, right? Because the second one has added some files And as they're running, they're going to make modifications to the file system as data is stored in the database. Those will be added in this blue write layer on top. But they're sharing a lot. They're sharing the base image as well as the Elasticsearch and Java modifications to that base image. So this creates some efficiency in sharing base images. If you have more than one container that are pretty similar running on the same physical machine. Now, Linux has good support for containers because it has built-in support for isolating processes from each other. And Docker makes use of this to implement containers that look like they're running their own Linux operating system. In addition, Docker provides the toolchain for compiling Docker files, this layered file system I was talking about, the central image repository, Docker Hub, as well as Mac and Windows runtime environments that run Linux on a virtual machine. And then again, it makes use of the Linux container functionality, which is called LXC or runc. I think it's the older version of it. So with containers, the containers don't see each other. They don't have access to each other's files. A container doesn't know that it's running with another container on the same physical machine. But unlike a virtual machine, they might feel each other's effects because they're actually dynamically sharing memory and CPU. Unlike a virtual machine, you're not pre-allocating a certain number of RAM megabytes or CPU cores to each image. They just kind of run at the same time, similar to processes running on an operating system. If you want to learn more about Docker, you can check out these links. So when you create a container, you need to deploy it somewhere to run it. Now you can, like I said, if you download, you can download Docker and run containers on your laptop. Deploying it to the cloud, I think there are two basic options you have. One is more self-managed, and the other is more automatically managed. So if you just have a pool of virtual machines, a cluster of virtual machines, like let's say EC2 instances, Kubernetes is a software for managing containers. It calls itself a container orchestration system, which would deploy containers to that cluster. And the benefit of this is that you can run it on your own hardware, as well as you have more control of being able to SSH into the virtual machines and do debugging. The downside here is that you have to control the number of virtual machines in your cluster. There's a trade-off here where if you have too few virtual machines, then you're going to be overloaded. Whereas if you have too many virtual machines, then they won't all be. Some of them will be idle, and you'll be wasting money, right? So if you don't want to have to manage that cluster size, and you don't want to install Kubernetes for managing running the containers on that cluster, then you can use managed container infrastructure, such as Fargate or container instances. So with these systems, basically you're just providing your container to a cloud provider, and that cloud provider has its own system like Kubernetes running across its huge data center to deploy your container somewhere. We don't care where. You just specify the CPU resources and RAM you want to reserve for it, and it kind of manages it for you. Okay. The only downside here is that you don't have as much access to SSH into the virtual machine to debug it and configure it. But the plus side is that it's more elastic, and you pay only for when your code's running, and you have access to a greater pool of resources to use more dynamically. If you really need to scale up quickly, you can do that on a shorter time frame than if you had your own physical machines, or even if you had your own virtual machines they had to spin up. Okay. All right, so comparing the two virtual machines and containers, they both are platforms for running code. The startup process, if you look at the process for launching each of these, you can see some of the differences. So with a virtual machine, if we want to launch a new virtual machine, if we have an image for that virtual machine, we first have to copy that disk image to the virtual machine monitor, to the hypervisor to run it. We have to reserve some CPU and RAM on that machine to run the virtual machine. Then we have to boot the virtual machine operating system. And that third step in particular is going to take a significant amount of time. With a container, we would start with a Docker file. We'd copy that Docker file to the host. The Docker file itself would probably include an instruction to copy some code along with it, or it could potentially be bundled along with the Docker file. The Docker file would probably download a base image, which is similar to copying a disk image, except it's probably smaller than a virtual machine image. But notice that if the same base image is already on that physical machine, then you can skip that step because the Docker layered file system allows it sharing. You would run through the setup commands in the Docker file. That could take a while. The amount of time it takes to do that, for example, to compile a program from source, that could actually take longer than booting a virtual machine. Or it might take less time, depending on how much is happening there. And then finally, you run the application specified in the Docker file. Okay, we were just talking about containers. Serverless functions are another approach to packaging code, which allows you to totally abstract away the platform on which your code runs. Now, this is a quite different approach, and it imposes a lot more constraints than the previous approaches. But what it does is it makes it much easier for your code to run anywhere in the cloud. So you don't necessarily know where it's running. You just know that it'll run somewhere in the cloud. You let the cloud provider manage that for you. The actual underlying computing platform, the hardware, that's not something you worry about. You don't have login access to the machine where it runs. You just write some code. You write the code in a language that's supported by the serverless function platform. For example, Python's a common choice. And you provide that code to the cloud provider as a serverless function. So the particular name you might see for these is on Amazon Web Services. These are called lambdas. So you create a lambda function, but also this concept exists not just on Amazon, but also on the other cloud providers like Azure. You can even write out the code in a web browser in the web console for your cloud provider. And that code is run somewhere later. Okay. These have to be much simpler applications because the code is all kind of like self-contained. If you have any dependencies, they have to be bundled in your app. So in other words, like if you're using Python and you want to use third-party libraries, you have to pip install them into into a subdirectory in your project and kind of like bundle that whole thing together and ship that, provide that as a Lambda. And these serverless functions are stateless. They have to be stateless because they're invoked, they return, and then they finish. We don't know where they're going to run. We don't know if they're going to run in the same place, so we can't make use of things that happened previously. You can't run command line processes and things like that. There's no environment at all. There's just like the language you're using is all you have available. And you don't really have a file system. You do get a temporary folder you can write files to, but that doesn't give you much power. Right. So the benefit here is that the code, it's the constraints placed on the code. In other words, that you can't rely on a lot of outside environment, outside applications, outside libraries, except literally the code you provide. Because of those constraints, it's much easier to start it up somewhere else. It also means that it can run on a pretty the cloud provider can provide a uniform environment for everyone's serverless functions to run. So your code can easily be spun up on that environment quickly without creating a container or virtual machine. Remember, the containers in virtual machines that are designed to encapsulate all the different oddities of your environment that might be necessary for your program to run. Things like libraries and command line tools and databases that might have to be running on the machine. The approach with serverless functions is you just assume that those things are not available. You don't allow those things to be used. Just provide a very simple, basic language environment for that code. Okay, so I used Python as an example. Java is another common choice, like a Java jar. Package jar is an ideal package for a serverless function. It runs on that standard Java virtual machine environment. If you're using just the standard Java libraries, then that's a very uniform environment that can be made available to lots of different tenants. Okay, so The way serverless functions work is you provide your serverless function to the cloud, right? You either you somehow upload it to the cloud, right? And you have some sort of cloud configured event to trigger or call the function. I'll talk more in the next slide about what that could be. When your function gets triggered, the code has to be deployed somewhere. I mean, code always runs on a computer somewhere. I mean, it's not like there is a server. It's not truly serverless. The difference is that you're not managing the server, and you don't have to be aware of what the server is, or it doesn't have to be dedicated to you. It can be shared among many other tenants. Okay, so your code is deployed to a virtual machine, perhaps even inside of a container, who knows, along with other functions from other customers, probably, but those details are abstracted away. There might be a short delay in starting the function. In other words, if this is the first time that function has been called in a while, then it would have to be copied to a new machine, and that process of copying it to a machine is called a cold start. But if your function has been called frequently, it probably is already on some machine somewhere in the infrastructure, and therefore it can be invoked quickly. Yeah, so your function is deployed on as many machines as necessary, not just one machine, but as many as necessary on demand. So if you have you could have a serverless function that is run thousands of times at once in parallel on thousands of different machines. The infrastructure is shared by all the different tenants in the cloud, so it's very there's a lot of horizontal scaling that's possible that you don't personally have to manage. You're not allocating specific machines to run the code. It's just you're just giving permission for the function to be invoked, and you're creating some kind of triggers or events that call the function. You're creating some connections to the function, which we'll talk about later. On Amazon, the Lambda functions that they provide for serverless computing are limited to running no more than 15 minutes, so that's one limitation. And notice that, like I said before, your code is deployed to some kind of virtual machine when it's run. That association between your code and a virtual machine is a short-term association. Eventually, it'll be migrated away for someone else to use the machine, right? But it's really not your concern, and it's really up to that whole process is a black box to you. You don't really care how it works as long as your code runs somewhere. So one of the downsides of this approach is that you're using a particular environment that's uniform, but it's probably customized to the particular vendor. So for example, with Amazon, you're using Lambda, and the particular Python environment or Java environment they provide you is a little different. It's not just the way that you invoke your functions, the way parameters are passed in is specific to Amazon. So there's a little bit of, there's more vendor lock-in when you're using serverless computing, serverless functions, than there is when you use containers or virtual machines. Because containers and virtual machines are technologies that will work on any cloud or even on your own infrastructure if you want. Serverless functions are kind of tied to specific runtime systems that are different for each cloud provider. That's one of the downsides. To invoke a serverless function, there are a few different ways that would happen. This is not an exhaustive list, but it gives you an idea. All right, so remember, the first thing you do is load your code in the cloud. So you might copy and paste it into the user interface for the web interface for Amazon Web Services, or you might upload it from the command line or something like that. Once it's there, it's ready to run, but it's not running yet. Something has to trigger it, right? Because it's not on a server yet. Something has to cause it to get invoked. An example might be that you, as the administrator, you can click a button in the Lambda console to launch a particular serverless function. So you can start it manually. You can provide certain inputs to it, just like any other function in a programming language. There are inputs to your serverless function. You can provide some inputs and click a button to run it. Okay, that's kind of a simple, that might be useful for testing. Probably in practice, that's not something you do very often. Some piece of your code can call into the Lambda API to invoke a function. So for example, if you have an API, like some back-end application running, like a microservice that handles a request from a user, and one of the things it might do is trigger a handler. It might invoke Lambda to handle to do something, right? So you can use the Lambda API as a gateway to run your serverless functions using your Amazon credentials to sign your requests. You also can have client requests handled by Lambdas if you're using the API gateway on Amazon Web Services. So the API gateway is like essentially a load balancer that's configurable to allow you to define different paths and methods. So like, get/account, for example, might be an endpoint you could define there, and you tell the API gateway how to handle that request, how to route that request. In other words, you can connect each request to a particular Lambda, a serverless function, to handle that request and give a response. Okay, so you actually can create a serverless backend by combining the API gateway with a bunch of serverless functions or one serverless function that implements that REST API. Okay, and notice that your serverless functions, just like any other code in Python, Java, whatever language you're using, it can make connections to databases, it can connect to queues, it can do all the normal things that your backend code would do. The difference is that it's not permanently associated to a particular machine, that's auto-deployed as needed when it's invoked. Another way to invoke a serverless function is through a CloudWatch event. This is a way to, like, for example, if you want something to happen periodically, you can create a CloudWatch event, kind of like a cron job, in the cloud to invoke that Lambda function with a certain schedule. You also can have some of the managed services on Amazon Web Services, like S3 or SQS. You can configure them to trigger Lambdas when certain things happen. So, for example, with S3, remember that's the scalable distributed file store that Amazon provides, or like the object store, I think they call it. You can configure that to run a Lambda whenever a new file is stored in a bucket. So, for example, if you're storing images, it might be useful to convert from full-size images to the smaller thumbnail previews. That work of conversion might be implemented in a Lambda, and it could be triggered by a new full resolution file being stored in an S3 bucket. SQS is the simple queuing service, Amazon's managed message queue. You can configure that to run a Lambda to handle the messages that are added to the queue. And there are other services that can be configured that way. So in other words, Lambda's kind of like on Amazon. It's there. A lot of their services are designed to be able to do things with Lambdas. You can connect different services with Lambdas. But you also can use these kind of like API gateways and the API for Lambda to invoke them in other ways. All right. Here's just a little picture I found that I thought was a little bit helpful in showing different ways Lambdas can be invoked. So on the bottom, we're showing the Lambdas. And in the first case, we have an API gateway, which is like a load balancer that's configured to have a certain REST API endpoint routed to this Lambda function. So this Lambda function will generate the response to the GET requests for /order. This connection can be made in the configuration for Amazon API Gateway. Also, asynchronous events include, for example, I mentioned when files are added to S3, that at some point there's a queue of events that are created, and those are handled by Lambdas, can be set up to be handled by Lambdas. And also, like other kinds of data stores can be connected. Like you can set up DynamoDB to have a Lambda function that processes new entries, for example. All right, so serverless functions I kind of view them as an alternative to either containers or virtual machines. And what they're really good for is infrequently executed code and batch processing. And another way to describe that would be to say bursty workloads. By bursty, I mean sometimes it's idle, sometimes it's really busy. Sometimes you need like dozens or hundreds or thousands of different tasks working in parallel. At other times, you need much fewer, maybe even nothing is happening. So if your workload goes up and down a lot, serverless functions are a great way to handle that, because you don't have to like choose one size of infrastructure. You don't have to say like I'm going to have 5 machines dedicated to this task. Rather, you just let the cloud provider provide the infrastructure that's needed to deploy that code when it runs. And it might be running. So when the code is not running, you don't pay at all. When it's running on a lot of machines, you pay a lot. But you can get a lot of parallelism and get the work done really quickly. So for example, if you are doing document processing and you have a lot of new documents that are created, you could, instead of going through them one at a time on a virtual machine, which might be the typical approach, that would allow you to like save money because you have one virtual machine that since you're paying for the whole time it's running. The most efficient way you want to keep it busy, but not have it idle. So you have to spread out the work over time to make good use of it. With serverless functions, you could just have a sudden burst of activity where for 30 seconds you have thousands of machines working for you to process those documents, and then they stop working. And for the rest of the day, you're paying nothing. I mean, you paid a lot of money in that 30 seconds. That per second charge was very high, but it was only for a short amount of time, right? So and because this infrastructure is shared by lots of users, the cost to you shouldn't be greater than spreading it out over time, right? So you get the benefit of greater elasticity than you do with virtual machines or even containers. Okay, so the key thing is no resources are wasted while the code is idle because it's not deployed to a machine. It's serverless. It's not connected to a server. Serverless functions, because they're constrained to work on a very uniform platform that's like the same as everyone else. Basically, everyone else who on the cloud who's using that flavor of serverless function. Like if you're deploying Python serverless functions, everyone's Python serverless functions pretty much are using the same platform. You can spin up those functions in just a few seconds or like half a second or a couple seconds. All you have to do is copy your code to a machine. I mean, you're not doing this. The platform is doing this for you. The platform copies your code to a machine and your application starts. Like it's just like running a process. Like you don't have to boot up a new virtual machine or allocate a new virtual machine. That would take several minutes. You don't have to start up a container. Starting up a container can take several minutes if it involves, compiling code or installing dependencies and stuff like that. Okay. But there's this trade-off, of course, between the uniformity. The environment you're running in is very kind of impoverished and uniform. You don't have the libraries available. You don't have command line tools, things like that. Right. Okay, so comparing these three platforms, we have at the left virtual machines. Now here we have we have several operating systems running on a single machine through a hypervisor that is sharing the hardware between those two different virtual machines. We have applications running on top of those operating systems. This allows us to run to isolate processes, isolate applications from each other, and creates a very consistent environment because we can set up all of the the tools and command line tools, libraries, and other features. Anything that can be on an operating system we can configure there. The downsides of this approach is a high amount of space overhead, so we're bundling up a whole disk image just for an application. It can be slow to start and stop these things because we have to boot up the operating system. And if we want to scale the application horizontally, like to deploy more instances, that's something we have to manage ourselves. All right, we have to create another virtual machine. And we might also need additional physical machines to support more virtual machines if we're running the infrastructure ourselves. With containers, we get the same kind of isolation of applications running on containers. We get the ability to customize the runtime environment, just like we did with a virtual machine. But it was a little bit more lightweight because we actually didn't have a full operating system dedicated to each of these two. There's just kind of like the illusion of its own operating system that the container management system is providing. So, for example, you don't have different device drivers. Like with a virtual machine, you have device drivers interacting with a virtual device, whereas with a container, you provide when the application makes system calls that interact with a device driver, that's actually happening through one operating system that has one set of drivers and things like that. It's a little less configurable than a virtual machine. One of the benefits here is that you also can get automatic horizontal scaling if you're using a managed infrastructure like Amazon Fargate, or if you're using Kubernetes on your own infrastructure. With serverless functions, we have less customization of the environment. Like the application runs in some kind of application manager. We don't have the ability to install libraries and command line tools and all that stuff that we get with virtual machines and containers. But it's much more lightweight. The startup time is really fast because we're not starting up a whole operating system or building a container. We have to work in one programming language. We're limited in the environment that we have. It has to be stateless, has to run for less than 15 minutes. And when we write these things, we kind of are locked in to a particular cloud vendor because this application manager you see, this orange thing, is provided by is different for each cloud vendor. Okay. I'm going to point you to a few tutorials that you can find on building. Amazon calls these modern cloud architecture designs. I guess I can quickly click some of these, but basically these architectures make very heavy use of lambdas and also a Fargate for deploying containers, things like that. So these are good examples of how to use serverless functions in practice. I mean, this isn't the only way to design an architecture. I think Amazon really wants to push serverless functions because it creates vendor lock-in, and you're kind of stuck using Amazon, right? You can see how Amazon is used. Lambdas are used in multiple places here, as well as other like very Amazon-specific versions of different tools. Okay. But anyway, regardless of the fact that these are very tailored to a particular vendor, they're examples you can look at. Yeah. I mentioned that there's a limitation that lambdas can only run for 15 minutes. If you need something that you want to be deployed automatically on demand, but you want it to run for more than 15 minutes, you can deploy a container to Fargate on Amazon, the Elastic Container Service. Okay. And this article talks about that. All right, so the main things I talked about today were virtual machines, containers, and serverless functions as three different computing platforms that provided different levels of abstraction, different ways to customize the environment, and different experiences for running the code, basically. With virtual machines, I mean, and all these, and these are kind of chronologically in order in how they were developed, when they were developed. So virtual machines are really a fundamental technology behind cloud computing, what allowed EC2 to take off in 2006. So the virtual machines allow multiple tenants to share a single physical server, and you can think, so that's a way to operate, but it also is a way to distribute your applications, because you can build a virtual machine around your application and distribute that application as a virtual machine disk image that can then be deployed to any instance that shares the same generic hardware profile as the virtual machine was built for. Containers are a similar idea, but it allows you to like distribute the code in a much more lightweight way. So you just define a Docker file, which is a blueprint for the image. Instead of distributing literally the bits of the image, you can distribute this blueprint for the image. So you can basically compile the container image instead of literally distributing it. Although there are also images you can distribute as either a literal image or a Docker file that builds one. I think for your purposes, most likely you would be starting with a base image, a generic base image, and then you'd have a Docker file that customizes it with the libraries you need and that downloads your code to it. And that's an attractive way to bundle up your application so it can run anywhere, as long as someone has Docker running. Serverless functions are a different approach where the computing platform is kind of like simplified to the bare bones of just having the like language features available, no extra libraries or command line tools, and you have this huge pool of online resources in the cloud, online computers that are ready they're available to run your code on demand. So you ship your code in the cloud, you stage your code in the cloud. Your code is ready to run, but it's not actually running until it's triggered, until it's invoked. And when it is invoked, it can be invoked many times in parallel to scale horizontally to a huge number of machines. This gives you much more dynamic and fine-grained scaling than containers and virtual machines. You can use as many machines as needed when needed. And you actually you only are billed, I think, by like the millisecond. That's another cool thing. So with virtual machines, if you're creating an EC2 instance, you're charged by the hour, or maybe you might be able to pay for less than an hour. I don't remember, but it's like a pretty coarse grain chunk. And I remember in the very early days when I talked about managed server, like outsourcing server management, they used to bill people by the month. Virtual machines from EC2 were an improvement in that you could bill by the hour. Now, serverless functions is taking that to an even greater extreme, where you're billed by the millisecond, right? That's pretty cool, because you can run, for example, you might be able to run your code on 1,000 machines for like 10 milliseconds each, and it doesn't cost a lot, but you're able to get a huge amount of scaling. Although in practice, there's a cold start to starting up your serverless functions, which could be which is several seconds to copy your code and launch it. So that's a little bit of a contrived example. You wouldn't want to run something for just 10 milliseconds on 1,000 machines at once, but theoretically you could do that if you're willing to wait a few seconds before starting. There's a little bit of a limitation with serverless functions. Again, like I said, that there's a maximum runtime. I don't really know why they have that, to be honest. Theoretically, that's not a limitation. That's more of just something they've implemented as a policy. Okay, hope that was helpful. See you later.